Okay, thanks. Thanks, June, again for the very nice talk. We can go ahead and with our second speaker, Joachim. Hello.
Hello, hello.
Do you actually pronounce well your name, Joachim? Because I always get messed with German and like Russian, like kind of like pronunciation.
No, that's absolutely all right. The really correct pronunciation is Joachim, but the sound is
Joachim. Okay.
Does not exist in many languages, so Joachim is perfectly fine.
No, I'm learning Hebrew, so it's like Joachim.
Oh, well, then
I can live with
many
it.
more
I can
similar
live with
sounds.
It. Exactly. So you can share your screen already, I think.
Yep. Let me do precisely that. So there it is, and now should be full screen.
Okay, perfect. Can you move your cursor just to see if I see it? And
I don't think you see the cursor because I don't see it.
Okay, but you don't need it. If you don't need it, that's fine.
Anyway. I know I don't really need it, no.
Okay, perfect. So I think that we can start the recording now for this second talk of the day. Let's see, let's give Minds people the time to start the recording.
I think the recording is already in progress, isn't it?
Ah, it already is progress? I didn't notice the new recording.
Yes, it's in progress. It's in progress.
Okay. Okay, perfect. So let's start this second talk. We are very happy to have Joachim Kopp from CERN and Minds actually also, that will talk about dark matter as destroyer of the world. So please, Joachim, please take the stage.
Okay, so well, thank you for inviting me to this wonderful workshop. I've already learned a lot, and I really appreciate the good discussions. The organizers have proposed to me to talk to a paper we published last year, which was called Dark Matter, Destroyer of Worlds, and which is basically about the possibility that dark matter accumulates in celestial bodies, forms black holes in there, and might eventually destroy these celestial bodies. So, in order to walk you through this idea, I'll first introduce the kind of dark matter that we are considering here, which is in particular super heavy dark matter candidates. I'll then talk about the processes by which dark matter can get captured in stars and planets. Then after it has been captured, it thermalizes with the surrounding matter. Finally, there's the possibility that it collapses into a black hole, and I'll discuss this collapse and the subsequent evolution of that black hole. And finally, in the last part of the talk, I will comment on experimental signatures and then set actual limits. Okay, so let's start by discussing super heavy dark matter. You've all seen this plot in one form or another. This one here is from a recent APEC report that shows that dark matter can exist in a wide range of masses. And it's not even complete because it stops at M Planck. And there are, of course, dark matter candidates like primordial black holes that can be much heavier than M Planck. But anyway, this is the more particle physics type dark matter, which has a rich repertoire of ultralight dark matter candidates, most prominent, of course, the axion and axion-like particles. Then there is the more vanilla mass range where conventional WIMPs, for instance, live. So by WIMP, I mean a particle whose abundance today is set by a thermal freeze-out process. And then there is what I will call super heavy dark matter in this talk. That's the mass range above the range of conventional WIMPs. Conventional WIMPs cannot exist there because the annihilation cross-sections required to set their abundance would need to be too large to be consistent with unitarity. But that's precisely the region that we want to look at. And it isn't the case that there are no dark matter candidates there, but there are certainly much fewer than in other mass ranges. As I already said, the reason for this is that conventional freeze-out doesn't work above order 100 TeV. That's called the Grist-Kamionkovsky bound. And it basically says that if you try to push the mass of a conventional WIMP heavier and heavier, you require larger and larger annihilation cross-sections in order not to overclose the universe or produce an overabundance of dark matter. And these large annihilation cross-sections will eventually be inconsistent with unitarity. However, there are, of course, other mechanisms by which dark matter can be produced even in that mass range. One of them being various kinds of freeze-in directly after inflation. That includes the possibility that the inflaton decays directly to dark matter. There's the possibility that the dark matter is depleted at a first order phase transition. That's called filtered dark matter. And there's a number of composite dark matter candidates that can live there. This is already the final result of this talk, and I'm already showing it to you here in order to tell you what we are aiming for in the end. So this is a plot that shows the usual dark matter direct detection plane, dark matter mass versus dark matter nucleon scattering cross-section, except that the mass range that we are focusing here and the cross-section range that we are focusing here is very different from what you usually see. So the usual version of this plot lives outside this panel here in the bottom left corner. Because here we start at a mass of already a PeV and go and go all the way up to the Planck scale. And the cross sections here are also much larger than what you typically have in mind for weakly interacting dark matter particles. I'm not going to explain the colored exclusion limits here because those are the ones for which I first need to introduce the formalism. Those are the limits that this talk is about. But I want to tell you already about the more conventional ways to look for such super heavy dark matter candidates. Of course, dark matter direct detection still works even for heavy dark matter. It's just not as efficient. Therefore, and it's not as efficient, first of all, because these super heavy dark matter candidates are less dense, and also because the kinematics is less favorable. So the recoil energies you generate are smaller. The limits down here labeled xenon 1 ton and DAMA, these are the direct detection limits. The lower edge of these limits comes about simply because at too small cross sections, the rate is not large enough for these experiments to be sensitive. The upper edge comes about on the one hand because the dark matter particles have to reach the underground detectors in the first place. And if they scatter too strongly, they will simply be absorbed before. And in addition, there's also the problem that dark matter may scatter multiple times in the detector. And when that happens, that's a signal that's typically rejected by direct detection experiments. There is a band, this gray band up here in gray is a limit from the heating of interstellar gas by dark matter scattering. So if the cross sections of dark matter nucleon scattering are as large as shown here, then dark matter would deposit some of its energy in the interstellar gas, heating it. And since we observed there is very cold interstellar gas, that would be inconsistent with observations. Finally, as for almost everything in particle astrophysics, there's a constraint from the CMB. In this case, the physics behind this constraint is that if dark matters and baryons scatter efficiently, that of course affects the evolution of density perturbations prior to recombination and also after recombination. So the CMB is also a sensitive probe here at the very largest cross sections. Okay, and as I said, the colored limits, these are going to be limits from dark matter capture in the sun and the earth. And I'm now going to talk about how these limits are derived. So we first need to talk about how dark matter could end up in the sun or the earth in the first place. So we have to talk about dark matter capture. Here is a cartoon of what a typical capture process looks like. Dark matter comes in with some velocity at infinity. It gets accelerated in the gravitational field of the sun or the earth. And then it enters the body with this higher velocity. And then if we are lucky, it scatters once or multiple times inside that body. And eventually it will leave it again. And if by the time it leaves the sun or earth again, its velocity has been reduced to a velocity less than the escape velocity, well, then the particle will remain captured. In particular, it will end up on an orbit that typically is still relatively large, crosses the sun or the earth, but also has a significant part of its trajectory outside. But then once the particle is on this orbit, this means that during every revolution, it will pass through the sun or earth again, and that will lead to further energy loss. And so over time, this orbit is going to get smaller and smaller and smaller until eventually it will be fully contained inside. We're going to talk about that later. But let's first talk about this initial capture process. The relevant physics quantity for this process is, of course, the dark matter capture cross-section. And we are going to focus mostly on dark matter scattering cross-sections that scale as the mass of the target nucleus squared. That's just the same as for conventional WIMPs. So you can imagine that this is an elementary particle that just happens to be very heavy and scatters coherently off all the nucleons inside the nucleus, hence this A square scaling. And there's also a kinematic factor that depends on the ratio of the mass of a particular isotope over the mass of a nucleon. And so in the limit that we are going to consider, namely where the dark matter mass is much heavier than the mass of a typical atomic nucleus, taking all of this into account translates even into an A to the 4th scaling. So the scaling, so the dark matter nucleus cross-section is A to the 4th times the dark matter nucleon cross-section. From the cross-section, we can then derive the energy loss rate of the particle as it travels through the sun or Earth. That's of course given by the cross-section times the number density times the velocity times again a kinematic factor that scales as the velocity squared. We have in our paper, we have also considered a somewhat different type of scattering, namely a scattering with essentially a geometric cross-section. Geometric cross-section, what we have in mind there is a dark matter object that is really geometrically much larger than an atomic nucleus. So this is typically the case, for instance, for some large composite objects of dark matter. So some let's call it bubble that contains lots of tightly bound new particles that scatter off the nucleus as a whole with a cross-section that is so large that if the nucleus hits that object, a scattering is guaranteed to occur. So it's just the geometric cross-section. It's really the area of this object, if you look onto the area of this object projected onto the scattering plane. In that case, the scattering has still a similar form. It scales as the density of the target times the cross-section times the velocity to the 3rd power, but there is not these mass ratio factors. As I said, this is something we considered in our paper, but in my talk, I'll focus on the more conventional scattering. That is similar to what you're used to from conventional WIMPs. Okay, so when you go through the steps of the calculation, what you find is this plot. The horizontal axis here is the dark matter mass. The vertical axis is the dark matter capture rate in the number of captured dark matter particles per second. Note that both axes in this plot are heavily logarithmic. The horizontal axis is so because this works over a vast range of dark matter masses. And from the vertical axis, you can see that depending on the dark matter mass, the capture rate changes quite rapidly. The quantities that enter this calculation is, of course, the density profile of the sun and the Earth, the dark matter distribution in the sun's or Earth's rest frame. That's something one needs to be careful to work in the correct reference frame. And we are also taking into account the possibility of multiple scatterings. In that sense, the formalism that we are using here goes beyond the traditional formalism by Gould et al., which considered only the case of single scattering, which is appropriate for conventional WIMPs, but not for these super heavy dark matter candidates with super large cross sections. Now, if you look at those curves, you notice that there is a characteristic change in slope. And that's because we are going through two different regimes here. Namely, for relatively light dark matter, where light here means a TeV to a PeV, maybe an EeV, that's the regime of efficient capture. So in that regime, almost all dark matter particles are captured. So essentially, you can imagine the sun or the Earth moving through the dark matter halo like a vacuum cleaner. Everything that crosses its path will be captured. At higher masses, capture becomes less efficient. And in that case, only a rather small fraction of the dark matter particles is captured. And that's why the curves become significantly steeper there. And you see, of course, in that case, there's also still some dependence on the scattering cross-section, which is given here in the labels of those curves. Whereas when the dark matter captures everything, then there isn't really any dependence on the exact cross-section anymore. Okay, so now we've captured some dark matter. What happens next? As I already mentioned, the dark matter particles will initially be on an orbit that crosses the star, but also they will also still spend a significant fraction of their time outside. But after they cross the star multiple times, their orbit will eventually shrink and will eventually be contained inside the star. So this thermalization process is effectively a two-step process. The first phase is when the dark matter particles are still on the large orbit that is mostly outside the star. And the second part is scattering when the dark matter particle is entirely contained within the star. And the end point of this process is dark matter particles that are thermalized with the surrounding matter. So they are still bouncing around the inside of the star, but they do so with a thermal velocity at the same temperature as the surrounding matter. So these two phases require slightly different formalisms. The first stage, the one where the dark matter is still mostly outside the star, the way we calculate this is we calculate the average energy loss rate per scattering. That's just from kinematics. We take into account the orbital period of the dark matter particles and the optical depth of the orbit, which just means the number of scatterings per crossing. With these quantities, which can all be evaluated relatively straightforwardly, we can write the average energy loss rate as the optical depth times the average loss per scattering divided by the orbital period. And then what we have there is essentially a differential equation, which we integrate from the initial energy, so the energy that the dark matter particle has immediately after the first scattering, to the final energy, where the final energy is the one where the orbit is entirely contained within the star. By doing so, we can get an estimate for how long it takes for this first stage of thermalization to complete. We know that it will eventually complete, but we are interested in how long it takes to complete, because, for instance, if it took more than a few billion years, then it would never have completed during the existence of the solar system. But what we find is that the duration of this first stage of thermalization is given by the quantity that's shown at the bottom of this slide. And if you look at this, you see that the benchmark values for the mass that we've chosen here is relatively low for our standards, and so is the value for the cross-section. And in particular, if we plug in the large cross-sections that we are ultimately going to talk about, then this first stage of thermalization will really happen very, very rapidly in less than a year. So basically instantaneously on astrophysical timescales. And that's reassuring because that means we can forget about the details of this process. We just know that it will complete very, very rapidly. So then enters the second stage of thermalization. There are two parts to this, namely when the second stage of thermalization starts. So when the orbit has just been completely contained inside the star, then the dark matter particles will typically still be moving much, much faster than the surrounding matter. However, they will continuously slow down, and eventually they will be moving much more slowly than the surrounding matter because they are so heavy. They are much heavier than the atoms that make up the star. So once they approach the same temperature as the atoms, their velocity will be much, much lower. We call the first regime the inertial regime, the second one the viscous regime. And because the viscous regime is the one where things progress much more slowly, we'll use that one for our estimates in order to be conservative. And once again, our goal is to estimate the time scale for the second stage of thermalization. And we get here an expression that basically depends on the scattering rate and a logarithm that involves the initial and final dark matter energies and the gravitational potential. And this part of thermalization, it takes longer than the first stage, but it can still complete over the lifetime of the sun and the Earth. I'll show more about this in a plot. Finally, the end point of all this is that the dark matter particle has been completely thermalized with its surroundings, and the dark matter particles that have reached this stage, they form a virialized dark matter core. Virialized means they satisfy the virial theorem, which says that twice their kinetic energy is minus the potential energy. And that's basically the state that a system is in where particles frequently interact with one another. We can estimate from the virial theorem, we can estimate the radius of this core. I'm showing two estimates here. The upper one is characteristic for the sun. The lower one is characteristic for the Earth. Once again, for a dark matter mass of 10 to the 7 GeV, we find that the dark matter core for the sun is a mere 30 kilometers large on average for these super heavy dark matter particles. For lighter dark matter particles, it can be much larger. And for the Earth, it's even only 2 kilometers. So the dark matter is really in a very compact state at the core of the star. And that's why it makes sense to think about black hole formation, right? If the dark matter particle was much lighter, if it was only a GeV or so, then this core would be much larger, much more dilute, and it would be much less likely for it to collapse into a black hole. But if we look at the super heavy dark matter, then the dark matter core can be compact enough to collapse. That's the reason why this is most interesting for a super heavy dark matter. Okay, now let's talk about gravitational collapse and black hole formation. There's a number of conditions that must be met for the collapse to happen. The first one is there has to be a Jeans instability. The Jeans instability means when you have a self-gravitating system, then the free fall time, which is the time it takes a test particle to fall from the outside of the distribution to the center, must be less than the sound crossing time. So the sound crossing time is, well, it's exactly what the name says. It's the time it takes a sound wave to cross the object. Because it's an object where particles interact with one another, one can define a speed of sound, and then one can define a sound crossing time. And the sound crossing time is a measure for the forces in the system that counteract collapse, basically the pressure forces. So imagine you have this sphere of dark matter particles, and they try to collapse onto one another. Then because of their interaction, there will be a repulsive pressure. But if the free fall time is less than the time scale associated with these pressure forces, then free fall will eventually win. So the collapse can proceed. That's the first condition. The second condition is that the virial relation must have a solution at all. This is not the case everywhere in parameter space. And if that's not the case, then collapse cannot happen because virialization can't happen in the first place. And it turns out that this is a stronger condition than the Jeans instability condition. And finally, if the dark matter particles are fermions, then there's also Fermi pressure that must be overcome. If they are bosons, there's of course no Fermi pressure constraint. However, if they are self-interacting bosons, then the self-interactions have to be overcome. And it turns out that that constraint is very similar to a Fermi pressure constraint. So for practically every dark matter candidate that is of interest to us, there is some sort of constraint there as well. Okay, once again, we are interested in how long it takes for this collapse to happen, because if it takes longer than the age of the sun or the Earth, then it will never have happened yet. The way we calculate this is by very similar arguments as the ones we used for the second stage of the thermalization process. So we start from the initial energy of the dark matter particles and we integrate a differential equation all the way to the point where a black hole forms. Except that now the viscous and inertial regimes are inverted, right? Dark matter starts in the viscous regime where its velocity is much less than the velocity of the surrounding matter. But as collapse progresses, dark matter particles will be accelerated. So they will end up, just before black hole formation, they will end up with velocities much larger than the surrounding matter. So the calculation can be done. And in fact, the resulting formula that we find is quite similar to the one we found for the time scale of the second stage of thermalization. There's again this prefactor times a logarithm. So in that sense, what this shows is that if there's enough time for the dark matter particles to thermalize, then there's also enough time for them to afterwards collapse into a black hole. Okay, this was a lot of words and a lot of formulas, so let me underline this with a plot. The plane that we are showing here is again dark matter mass versus dark matter nucleon cross section, so the standard direct detection plane. So now I'm not showing any limits yet. What I'm showing here is the various time scales. The gray curves show the black hole formation time. So you see that as we go to smaller dark matter masses, it takes longer for the black hole to form. Well, that's because the dark matter core is less dense. And if we go to too small cross sections, then again, it takes much, much longer for black holes to form because it takes much longer to accumulate the required amount of dark matter. In red, we show the black hole evaporation time, because after the black hole has formed, of course, the black hole will start to evaporate. And if it instantaneously evaporates, then we have no way of detecting its existence. You see that for the heaviest dark matter particles, the evaporation times are very, very, very short. That's because these are very small black holes, because the dark matter core then is so compact that after just a few dark matter particles have been accumulated, they will already collapse. But their total mass at that time is still very low. So the black hole that forms will be very light and will evaporate quasi instantaneously. As we go to lower dark matter masses, the black hole lifetime gets larger and larger and larger, until eventually below a mass of roughly 10 to the 12 GeV, the black hole will be effectively stable. It will never evaporate over timescales of a billion years. And as long as the star lives, it will maybe never evaporate at all because it accretes stuff faster than it radiates away energy via Hawking radiation. So what this means for us is the most interesting or the most dangerous regime is here to the left of this black dotted line or the leftmost red line, because that's where the black hole can stay at the center of the sun or the Earth and start consuming it. I'd also like to mention that here at very, very large masses, there is this purple region here, which says drift time larger than 10 to the 9 years. So what happens there is that dark matter particles interact so strongly with the surrounding matter that it takes them more than 1 billion years to diffuse from the outskirts of the sun towards its center. So in that case, already the formation of the dark matter core takes more than 1 billion years. And since the sun is only 4 billion years old, this means that black holes will never have time to form in this case. Okay, now let's finally talk about how we can observe all of this. Perhaps the most obvious signature would be if the black hole consumes its host. And from the fact that that hasn't happened yet, that the sun and the Earth are still there, we can set limits, because we can exclude parameter regions where we predict that the Earth or the sun could not have survived for 4.5 billion years. There's also the process of anomalous heating. As the black holes evaporate, they dump their energy into standard model particles. And other than the neutrinos, the standard model particles cannot leave the star, so they will heat it. Of course, for the sun, that doesn't make a difference because the sun is very hot as it stands. But the Earth is a relatively cold body, and we have a rather precise idea of how much heat the Earth radiates. And so we can exclude parameter points at which the total heat flux that would come from black hole evaporation would be larger than the observed total heat flux. The reason these limits are strong is because if dark matter collapses into a black hole and then the black hole evaporates, then basically all the energy that was previously stored in the dark matter is converted into Hawking radiation, is converted into heat. That's similar to when dark matter annihilates. And finally, the most novel signature that we talk about here is neutrinos that hasn't been discussed before. That's the neutrinos from black hole evaporation. As I already said before, when a black hole evaporates, it goes into all standard model particles, and that includes neutrinos, but neutrinos are the only ones that can escape. The characteristics of this neutrino flux are that it will have nearly a black body spectrum, because that's the spectrum of a black hole. And on top of that, there will be secondaries, right? In addition to neutrinos, black hole evaporation will also produce, for instance, hadrons, and pions decay to neutrinos. And from those decays, we get an extra secondary component of neutrinos that also needs to be taken into account, and that can be very large. The neutrino flux is directional because we have a pretty precise idea in which direction the sun is and in which direction the center of the Earth is located. Depending on the parameters of the model, the neutrino signal can be transient, because only at the very late stages of black hole evaporation, the neutrinos will have high enough energy to be detectable, right? The temperature of the Hawking radiation depends on the black hole mass, with large black holes, heavy black holes, radiating at a very low temperature, and small black holes radiating at a very high temperature. So if a black hole forms, then it may evolve for a while, radiating at low temperature, and then as it approaches the end of its life, the end of the evaporation, the neutrinos may pass the energy threshold for detection, and that would then lead to possibly transient signals. And finally, the neutrino flux is at least initially flavor universal, because black holes only care about the mass of a particle. They don't care about the flavor structure, for all we know. Okay, here's a plot. Or there are actually two plots. The one in the upper left-hand corner is the expected neutrino flux from black hole evaporation. The horizontal axis is the neutrino energy, the vertical axis is the flux, and the different colored lines correspond to different black hole masses. So if you have a real black hole, it will pass through all these stages. It will go from heavier to lighter, of course. You see the dashed lines have the characteristic black body shape, that's the primaries. But on top of that, there's a much, much larger component of secondaries that live at lower energies, however. So if you're using a detector with a sufficiently low energy threshold, then your flux will be totally dominated by those secondaries. And that's because for instance, if your black hole evaporation produces one very high energy quark, then that quark will hadronize, and the hadronization leads to many pions, and each pion will decay into a neutrino. And so for every primary quark, for instance, you get a large number of secondary neutrinos. That's why that flux is many orders of magnitude larger than the primary flux, but also at lower energies, because the energy of the primary particle, of course, needs to be shared among all the secondaries. On the bottom, in the plot on the bottom right, we have integrated over time. So in the upper left hand, this is the instantaneous spectrum if we take one snapshot of the black hole. But of course, in reality, we can't do that. So in the bottom right-hand corner, this is the spectrum integrated over a number of years. The dashed curves are essentially what you get from the spectra in the top left. The solid curves are what you get if you take into account neutrino propagation effects. That is most importantly neutrino absorption, because above energies of order at TeV, the Earth is no longer transparent to neutrinos. So no matter what you do, those neutrinos will not be able to leave the Earth. And in addition to that, there's of course flavor oscillations, and there's also processes where, for instance, as a neutrino propagates, it scatters. The scattering produces new leptons or pions. Those again decay into neutrinos, so you get an extra addition to the secondary flux. So that's all taken into account here in the bottom right-hand plot. Okay, and now we can compare all of this to experimental data. And that brings us back to the plot that I showed in the very beginning of my talk. But now let's talk about the actual colored regions, because now we can understand what those regions mean. So the yellow region here is labeled sun destroyed. So that's the region where in the 4.5 billion years that the sun has existed, a black hole should have formed in its center, and that black hole should not have evaporated, but should have grown by accreting more and more and more material from the sun. And so the sun would eventually have been consumed by it. This region has a sharp boundary at on the left, because at such low masses, the dark matter is too light for a black hole to form. You can see that in the plot that I showed you previously here, right? If you look here at the gray curves, that's the black hole formation time. So at some point, the black hole formation time exceeds 1 billion years, so there wouldn't have been enough time for a black hole to form. Right. The red region here is the region that's excluded by the heat flux from the Earth. So within that red region, black holes would form inside the Earth, but they would evaporate and heat up the Earth, exceeding the Earth's heat flux. The blue region is where the Earth would have been destroyed by a black hole forming at its center. And finally, the green region is the one that would have been excluded by that is excluded by neutrino observations. So you see that at present, this new observable here, the new neutrino observable, this only covers parameter space that has already been covered by others. But of course, there is hope that this may improve in the future. Now, let me explain a little bit better the shape of these curves. I already explained the left edge where there's not enough time for black hole formation. Notice that for the Earth, that limits it at higher masses because the Earth has less intrinsic gravity to assist black hole formation. The bottom edge arises simply because we need to collect, cool, and collapse enough dark matter, right? If the cross-section is too small, it will simply be unlikely that enough dark matter particles will be captured. The top edge comes from the fact that thermalization must be fast enough. As I already mentioned before, if that's not the case, then dark matter may be captured, but it will stay in the outer layers of the sun or Earth because the viscous drag force will be so strong that it will take forever for the particle to get all the way to the center of the star and form a possibly collapsible core there. So above the upper edge of these regions, that never happens. Once again, that cross-section is higher for the sun than it is for the Earth. Yeah, that's, I think, again, because the sun has more intrinsic gravity. Okay, that basically brings me to my summary, and my summary is, once again, this plot. So this is what this paper that the organizers proposed that I talk about is about these limits here and how they can constrain some of the parameter space that hasn't been probed or cannot be probed by any other means. I admit that that's not the vanilla dark matter candidates that you mostly read about in astroparticle physics lectures, but in my opinion, there's nothing wrong with such heavy dark matter candidates. And so that's an interesting avenue to explore. And yeah, from the point of view of our existence, I'm really grateful that we are not living in that region that's excluded by sun or Earth destroyed, because then we would never have evolved into humans. Okay, that brings me to the end of my talk with still a little bit time left for questions. So thanks all for your attention. I'm happy to answer any questions as best I can.
Thanks a lot, Joachim. This was very wonderful talk. I enjoyed it a lot.
Thanks, Eduardo.
Let's see if there is any question. So
Eduardo
has a question. Eduardo has a question, and I also have a question, but let's begin with Eduardo.
So if I understand, no, it's thank you for the very nice talk. I mean, it's exotic, but it's interesting. I mean, it's not excluded. So
thanks, Eduardo.
So if I understand it correctly, these neutrino bounds come from burst, right? Like you have the production of you have the collapse of these black holes all of a sudden in the center of the sun, and then they evaporate as soon as you produce them, right? Like you produce them very small.
Well, that depends on the exact mass that we are looking at.
Okay, I see. Okay.
The data set that we've used to set this limit was an IceCube data set that integrated over something like 3 years or so. And since we only had the integrated data available, we couldn't distinguish.
You couldn't see the time signature.
Yes, exactly. That's one of the reasons I said that's one of the reasons I said there's hope that these limits may improve in the future, because of course it is possible to do a time-dependent analysis and look for transients with much higher sensitivity than you can do for an integrated signal.
I see. And then probably this is a dumb question, but like, of course you lose a lot in terms of flux because of R squared, but like the sun age is like, I don't know, like 4-5 billion years or something like this. So if you look at stars like white dwarfs, for example, that are like, whose age can be like 5 billion years more, can you have a flux of neutrinos, like of a diffuse neutrino background coming from these black holes, or like the advantage of the sun being so close is so big that it doesn't make any sense to look at the diffuse of these neutrinos produced by black holes in the center of white dwarfs around?
So to be honest, we haven't done the calculation. I think we may have discussed it at some point, but we then didn't pursue this idea any further.
You also have the disadvantage, obviously, that it's not directional. But again, like I was just wondering if.
So my worry would be that, okay, that's different. That's a different energy range. But when you look at the limits on conventional WIMP annihilation, you can set limits by looking at the sun, but you cannot set limits by looking for diffuse flux, at least not limits that are as strong as they are by looking directly at the sun. And I assume the scaling would be similar here. So of course, there's a difference between white dwarfs and the sun, but I think that may actually go against us because white dwarfs have a much larger geometric size. So the amount of dark matter that they are passing through is less.
Well, yes, but of course, but like you have to integrate over their history, so they have different sizes. I was just wondering that like they stay there and they accumulated the dark matter like earlier compared to the sun. That was.
That's true, but that again depends on where exactly in parameter space you are. Because if you have black holes that evaporate relatively quickly, say over less than maybe a billion years or so, then what matters is more the instantaneous capture rate rather than the historical capture rate. Because the dark matter that had been captured when the white dwarf was still a regular star, that would have collapsed and formed a black hole maybe already before we wouldn't be able to see that.
Yeah. Okay. Thank you. I mean, I
thanks, Eduardo.
Okay. Any other question for Joachim? Otherwise, I go ahead. I don't see other eyes. People are shy, so I will ask. I have a couple of questions actually. So one is related to the fact that, so you're just coupling with protons, and so I don't know which kind of UV completion do you have in mind, but may you worried about like loop induced coupling to other stuff like photons, and so possible, for example, dissipation channel while you're doing all your stuff or not? Or you have in mind some models in which anything will be very suppressed?
So we didn't look at the possibility of loop-induced couplings. So what you're saying is that in a concrete model, you may have extra particles at these high scales, and
right, exactly. Yeah, it's typically the case, right? Also with dark matter, when you're doing some complete model and you couple to nucleons, right? You have to be careful, right?
But typically what dissipation would mean is that the dark matter would have an efficient path to lose kinetic energy. So this would only mean that thermalization and black hole formation might happen faster.
That will shift a bit your bounds, right? For example, or like you, or like the collapse could happen faster, true, or you can have also more bounds from cosmology. I don't know, because you're at some point you will start also emitting some.
Yeah, that's certainly true. So the bounds shown in gray here, they would certainly change, but that is definitely something we didn't look into, and we also didn't consider that possibility for our bounds. But as I mentioned, I think it would only help us, so it would make the excluded regions larger because it would make thermalization faster. So it might help us push a little bit to the left here. I'm thinking about if there's any way in which it could inhibit collapse.
Well, probably no, because like actually in star formation, typically you need like in POP3, right? You need
radiation
in order
right?
to collapse.
Yeah,
right?
radiation helps,
right?
Because you can get rid of angular momentum in that. Yeah.
Yeah, but on the other hand, this is a bit more complicated than that, because like in this case, like these cross sections are so large that if you have these interactions, whatever comes in comes out. So eventually, I'm not sure that you are actually having an enhanced collapse because you have dissipation through emission of photons. Because like if you can dissipate photons, you can also absorb photons. So eventually, I think that the time scale will not change dramatically. That's my guess.
Well, this is something that is not trivial, but I think that is interesting. Like, because in any UV completed model, you may have further interaction, and I'm not sure in which direction.
But like with protons, there is also the difficulty that protons are not elementary particles. So if you put them in a loop, there is the fact like.
No, but these are you always have.
Then you have to find a UV completion, but this is a sigma chi n, a very generic sigma chi n.
No, of course. But when you do this sigma chi n, of course, like Joachim has been doing, of course, like you still have to think a little bit, like if you want to go farther, right? Because if you couple to some quark, let's say, right, or some with gluons, the low energy will be different. So like. In any case, okay, that's fine.
Thank you.
I also have another question that is related to what.
May I just say one thing? One thing regarding your previous question? My worry, the reason I was hesitating is that if you have a strong coupling to photons, then there will be radiation pressure, and radiation pressure will assist the forces that like to inhibit collapse.
Yeah.
So I can't say how important this would be, but this is the thing that I would be worried about.
I think.
No, but exactly the point is that what I was thinking is that you are because of what I was worried about is that you are converting something that was giving you gravity, okay, like the dark matter, to something like radiation that could in principle push out. So this is when my question came to my mind. This was what I was worried about. Let's say. So this precisely. Maybe we can take a look at it, and it would be interesting. But that's fine. And also, like, I had another question that is related to what Eduardo asked too. Like, if there is any way in which, especially as you said, of course, I agree that if you go to larger masses, then it becomes like irrelevant to look at long-lived sources, let's say. But let's say we want to completely close this parameter space. So there is this white region left around 10 to the 6 GeV or so, right? That is like it's not difficult. It doesn't seem super difficult to close, right?
Yeah,
so
one of the things I would try there is the direct detection limits can in principle be pushed into that region, because as I said, I'm not sure what exactly the limiting factor here is, if it is multiple scattering or if it is absorption of the particles on the way to the detector. If it's absorption of the particles on the way to the detector, then you would look at dark matter detectors at the surface. But since I think the authors of the paper from which we've taken this have done this, I think it's more likely that it's multiple scattering. But of course, there's nothing wrong with doing a multiple scattering analysis in a dark matter experiment, right? There's no reason you have to reject multiple scattering events. You can include them. Of course, you'll have a somewhat larger background because multiple scattering is the signature of a neutron. But still, you can still require that your dark matter does not exceed that background, and that may push the limit further there.
Okay, fantastic. I mean, thanks a lot. I stole already a lot of time, so let's see if anyone else has other questions. I don't see any hands, right? Of course, we can continue our discussion during the coffee break if you're around, Joachim. Thanks a lot again for the talk. I think that we can stop this recording.